Well, hello and welcome to our webinar today. We're here to discuss battery charging in hazardous locations from both solar and wind sources. I'm Kyle Wilsey, a senior sales engineer with Morningstar Corporation, and I'm joined here today by Ken Kotelik from Primus Wind Power. They manufacture the air turbine line. So with so many people joining us today, we'll have to mute the participants, but if you do have questions and want to send them in to us by chat, you can do so at the bottom of the GoToWebinar window, and we'll try at the end to address as many as we can. If we don't get to everything, of course, we'll do our best to respond back to you in a timely manner at the end of the presentation. So let's get started. With about an hour, we'll split up roughly half and half between Morningstar and Primus, and leave hopefully between 5 and 10 minutes at the end for the Q&A. Just to give you a short summary of what we're going to discuss, really quickly, it won't be long-winded, just a quick history of Morningstar and the Sunsaver line. Go through the Sunsaver in particular, as it is our controller rated for hazardous locations. Talk about characteristics, features, some basic troubleshooting procedures, and then, as time permits, a little bit about MPPT and when you might choose an MPPT controller, even in an oil and gas site or other hazardous location where non-classified equipment is allowed. Then we'll get into hybrid system design, specifically with the air turbine line, and get into some discussion of its design, siting, regional and seasonal factors affecting choices for wind systems and hybrid systems, and a few images from around the world toward the end that just highlight some different and unique applications of solar and wind together around the world. Morningstar is a U.S. company. We've been one of the leading manufacturers of solar charge controllers and inverters for over 20 years now. The same ownership, same management, distribution partners, lots of loyal end users and dealers and distributors throughout the value chain. The last year we did our customer survey. Our customers in aggregate gave us an A rating for product quality. And of course, as many of you know, we've fielded quite a few controllers, many of them Sunsavers. We think about 3 million or more worldwide. That total's probably risen a little bit since publication of this slide, but definitely a global company, focused very heavily in oil and gas, warehouse locations in Los Angeles and Taiwan. One thing that we like to highlight is that we certainly hold plenty of stock, can always ship on a moment's notice to keep your businesses running. And on the product side of things, engineering over many years has yielded numerous patents and trademarks that I think you'll recognize throughout this presentation. Since our inception in '93, it took a couple years to launch the Sunsaver product line. That came out in 1996, and it's been a core product for us since then. We think about over 1 million Sunsavers have been fielded in that time, and have been keeping batteries in prime health and loads running in the oil and gas fields for about 20 years. So before we get started with the Sunsaver portion of the discussion, I just want to run a quick poll to ask everyone here today a little bit about their experience with the Sunsaver. So just to give you a couple choices here, if you could take a few seconds and just check as many boxes as apply to you. You've either installed the Sunsaver, maybe some of you have sold them, hopefully some of you, as we know, have purchased, and if you're new to the industry and don't know much about solar, what the heck is a Sunsaver? I'm getting some of the results here. Looks like quite a few of you are voting. Appreciate that. A couple more seconds here to get some sense of the distribution. Wow, so it looks like I'm going to go ahead and close the poll now. About 80% of you have voted. Looks like the vast majority have installed the Sunsaver, 61%. About a third have sold it in one form or another, and almost half have purchased one. So we've got a pretty experienced group here. It's good to know as we go through. Hopefully we'll have a little bit of something for everyone. You know, we've got a lot of ground to cover and really want to get through both the technical and kind of an overview of system design. So we'll jump right in. Oh, excuse me. So to give you a little history of the Sunsaver, you know, we'd love to see some pictures of your applications and your sites in the world. So if you could send them our way, if you do have anything to share about your longest lasting sites. You know, but I wanted to say first before we move on that, you know, it may seem to some of the newcomers that oil and solar and wind may be unusual partners, but you know, believe it or not, there's been quite a symbiotic relationship between these industries for decades. In fact, many of the first solar systems that were commissioned were done so at remote sites to power equipment in the oil and gas fields, and there really was no other choice but to turn to solar. So that's really what we're talking about here, is the off-grid industrial side of solar power, providing remote power, reliable power where there was really no other option. For us, the market continues to grow, even in this challenging time for oil prices. A lot of oil and gas producers are still focusing very heavily on increasing automation in their operations and reduce their operation and maintenance costs. Solar is a great way to accomplish that. So typically, what are we talking about running? I mean, we only put power into the field where a need for reliable DC electrical power is required. So we're generally talking about things like SCADA systems, probably most commonly RTUs, burner management systems for certain types of sites like the Profire that you see pictured here on the bottom left, all kinds of sensors, data logging equipment, and then transmission devices to get that sensory data sent out to a central control operation somewhere remotely. Not to mention the motors and pumps that move the liquid, gas, and other chemicals, often pretty highly volatile, around the oil and gas site. Typically, in a system like this Profire system, you know, the Sunsaver would represent usually less than 10%, sometimes 5 to 10% of the overall system cost, but it's relied on to keep much more expensive equipment like the Profire up and running continuously. You know, and if and when there were to be a problem with the PV system, you lose that critical load. The vast majority of the time, it's not the relatively low-cost Sunsaver that fails, but rather something in the design of the system or a failure in some kind of preventative maintenance procedure, batteries that would reach their end of life, something else that causes the system to go down. And when that happens, you know, big problems can occur. So to the extent that it's possible, we like to ensure the best battery health and obviously keep the system up and running. So to really boil it down to the most core functions of the charge regulator, you can see we're mainly regulating lead-acid batteries. This presentation won't focus so much on the new chemistries that are emerging in other industries. I think by the vast majority of all sites are still using lead-acid, although we may see that change in the future and are keeping a close eye on that. In these kinds of cycling applications, like you see pictured in this particular site, the primary job of the regulator is in a distributed solar environment to prevent individual batteries or battery banks from being either overcharged, given too much current, which typically isn't a problem, but more importantly, the undercharging. You know, that's really where systems go down or become at risk of going down, and it's also really bad for battery life. In practical reality, we are always operating somewhere in the middle. You know, there's never a time when the battery is consistently full for a long period of time or consistently down for a long period of time. You know, we're always operating in a partial state of charge environment. If and when the battery does become close to fully discharged, we have a feature of low voltage disconnect as a fail-safe just to manage the load to protect the battery from a permanent state of being irrecoverable. Again, that low voltage disconnect of managing a load when the batteries are low is truly intended to be a fail-safe. A lot of times we get questions about being able to adjust the LVD set points on our equipment, and we'd say, of course, in the worst case scenario, you could always wire a load directly to a battery and risk a pretty substantial failure of that battery system if the system is not sized properly. But certainly we'd always recommend that you do use the LVD terminals and keep things running as intended. We also try to give you a fairly rich data interface to work with a small set of LEDs, just to give you some indication of system status. But the one thing to point out here, and I think some of you have probably noticed already in this system, is that there just is not a substitute for proper design. There's only so much that we can do. We can work with the solar resources that are available to us and the battery bank size that's chosen. But if you happen to place a solar array facing obviously directly opposite the sun or behind equipment that can shade it, your performance will drop significantly. So to show you just a quick curve of what can happen in that scenario where you under design a system or have an issue with the placement of the solar modules, we're showing here on the bottom x-axis cycle number versus discharge capacity. A severely and chronically undercharged battery will always fail much, much faster than even a battery that's chronically overcharged. So again, can't emphasize enough that each system that's deployed with a Sunsaver is designed properly for autonomy, solar installation levels, load run time, but in the event that you do end up in this kind of a state, at least we will allow the LVD to protect the battery from being completely irrecoverable. So just a quick note about where the history of solar controllers has been. Before the Sunsaver was released back in 1996, the only choice was really a shunt type controller. And this is a very basic device that just diverted current away from the battery after the regulator recognized a certain voltage set point. Really, essentially a one-stage charging algorithm that shorted current away from the battery. Really simple. Problem is that it doesn't allow you to get a battery even close to a full state of charge, and it's not a great way to dissipate heat in an electronic device. Believe it or not, some of these systems are still out in the field today. That's pretty antiquated, but some still cling to the idea that this works, and it does. It doesn't. It's not going to damage a battery immediately, but you certainly won't get the capacity that it's rated for, and its life will very likely be diminished. So from the beginning, we have always offered a what we call a series PWM design, where the Sunsaver or other controller, Sunkeeper, is often used in these kinds of applications as well. We use this series design to directly control current to the battery in the power path. Sunsavers, Sunkeepers are all certified for use in hazardous locations. Typically that's a Class 1 Division 2 rating, groups A, B, C, and D, and the CSA 22.2 rating is also included with every Sunsaver that we make. Nothing has changed from the early days of the amperage choices. They will all come in a 6, 10, or 20 amp model, and either 12 or 24 volts DC, but not in a single unit. So you do have to know and specify which battery voltage you require for your particular system. The designing feature that identifies the Sunsaver and the Sunkeeper over others that we make and that allows us to maintain and achieve this Class 1 Division 2 rating is the epoxy encapsulation. This is a method we'll show here in the next slide of insulating the power electronics and the PCB, the printed circuit board, from external environmental factors like humidity and certain airborne particles that could certainly have negative effect on the life of the controller. Many regulator brands don't do this. It adds quite a bit of expense and even more time to the production process to both fill the controller with this specially formulated epoxy and allow it to cure properly. But it does give us the ability to offer a standard 5-year warranty, and often we see quite a bit longer design life even than the 15 years that we expect. With this kind of a feature, we have seen Sunsavers that have lasted since the day they were fielded. The second identifying feature of the Sunsaver is the conformal coating we use on the PCB before it's coated with epoxy. And this is actually something we do with all of our equipment. Without it, we really would have some pretty major issues with corrosion in any case where you have consistently high relative humidity or any kind of salt spray around a marine environment and such. It's again a cost adder for us, but lets us achieve that 5-year warranty and 15-year design life. So going back a few years, some of you might remember what we call the legacy Generation 2 Sunsaver model. It was a tried and true kind of bulletproof controller for many years. It worked great. It fit into the enclosure, didn't take up a lot of space, had a pretty wide range of amperage selections, and a really small footprint and easy wiring terminals. But it was fairly limited in its ability to, I guess you'd say, protect itself in the case of certain, system failures, shorts, overcurrent scenarios. Did have the hazardous location rating, obviously, but really couldn't do much beyond what it was given. It had a very specific connection order. You had to commission it and decommission it very specifically, and so it had some limitations. We created the Generation 3 version sometime around the end of 2012, early 2013, and really overhauled it. Went from an analog design to fully digital, microprocessor-based architecture that gave us a lot more flexibility to give it the protections that we thought it deserved, and that we were seeing come back as causes of failure in warranty. So I'll get into the specifics of the electronic protections, but wanted to hit on a few features that are new to this version. Everything you see today in the field that you're buying from off the distributor's shelves will be a Generation 3. I've seen very few of the older versions still trickling through, but they are out there, certainly fielded, and as they reach the end of their life, I imagine they'll be replaced with the 3rd generation. That includes multi-stage battery charging, so we've added a few extra charging states that I'll mention here in a few seconds. Self-diagnostics continually running, multicolor status LED, battery charge level indicators, and a couple other specific features to the industry that I'll talk about in a bit more depth. Unique to this version, this generation, is the 1741 certification from UL, and that's achieved when you use it with the included plastic terminal cover. Just to detail the electronic protections and emphasize the point that they're all reset automatically. These are conditions that result in a fault of the controller, not some kind of a critical error, but a recoverable state. Solar overload, load overload, both short circuit protection for load and solar, reverse polarity on either the battery or the PV, and any kind of high temperature or high voltage disconnect situation. There's really not much that you can do to the Sunsaver during operation to cause an issue, but there are certain few things that we certainly can protect against. The most common failure mode for most solar systems in the remote areas is always going to be lightning, and so we always recommend system level lightning protection. But within our control, that still sometimes occurs, is an over voltage on the input. For the 12-volt Sunsaver models, it only can accept 30 volts. For the 24-volt models, the limit goes up to 60. So if you wire a few panels in series versus parallel by mistake, you could run into some problems. But in general, if you follow commonly used design procedures, you shouldn't have an issue. The third and most important failure mode that I want to mention that is within the control of the operator is on maintenance. So with the third generation model, we said that connection order no longer matters. Disconnection order will not damage the controller. We still definitely recommend a certain procedure that's detailed in the manual, but the one thing that the controller cannot protect against is the removal of the battery during operation, which could result in a load spike, a voltage spike on the load terminals. When you remove the battery, you're removing the controller's power source, and this is limiting its ability to protect anything else after it effectively turns off. So if you have a high voltage on the solar array, it can be passed to the load. That can happen with, in a really short time period, milliseconds, and if you have a sensitive load connected, can really cause some problems. So this slide should look pretty familiar to most of you. All of our controllers follow some variation of this multi-stage battery charging algorithm. In the Generation 3, we've added an equalization option for flooded batteries, or even some of the up-and-coming AGMs that have a bit of a higher charge set point recommendation for regulation voltage, and a float stage. So for those applications that maybe only transmit occasionally, but we still need to reduce the regulation voltage to, we're usually around 13.6 or 13.7. The only selection you can make and change on this is the sealed flooded select jumper, which is shown here over on the right side. This kind of method is common for several of our controllers. Removing it turns the settings from sealed over to flooded. The controller is continually running a series of self-diagnostics. The third generation has 4 LEDs, 1 charge status, and 3 battery status lights. The temperature sensor shown in the middle looks a little different from the second generation, but does the same thing. It applies a temperature compensation factor for any scenario where the battery temperature might vary from 25°C, which is most all of them. I just wanted to show you also a quick indication of how those LEDs will give you, some basic feedback. On the left side, you'll see just the simple green-red indication. We're talking about the charging status light to the left of the temperature sensor, basically saying it's at night, everything's good with a green solid on for charging. If it's red, you have an issue. However, if it's simply steady and just flashing red, it's recoverable. If it's on solid with a slight flicker off every 5 seconds, then you could have a critical error. That's really important to differentiate. A lot of folks, I think, expect that the steady flashing might indicate an irrecoverable state. It does not. All right. With regard to the 3 battery status lights, you get an indication of a rough state of charge from battery empty, indicating an LVD situation, all the way up to a close to full battery, a slow to medium flash. That would indicate everything's good, no issues, and you can rest assured that the load is at no risk of turning off. If you have any of the flashing red indicators, again on the charging status light, these are the breakdown of conditions that you might see. Overloads, high voltage, or if it's solid, a damage condition that really means a replacement is required. If you see 2 lights flashing on the battery status indicators at one time, that's an indication of a specific condition that is again recoverable, but will clear itself as time permits. And into a couple of the last features that I just want to touch on real quickly that are unique to the Gen 3 and unique to oil and gas and hazardous locations is a dead battery recovery. In this feature we've added allows the controller to divert solar current to the battery even when the battery is below the 8-volt threshold to power on the controller. It will essentially let the battery or attempt to allow the battery to come back up with the solar resource that's available. It will only work, for those cases where the load uptime, is not critical. Often, I think these these extremely low voltages do initiate a service call of some type. This is intended for those extremely remote places where no one will likely make it to perform maintenance on the system. Power handling for sensitive loads. We've taken into account a lot of your feedback on how RTUs may have a narrow voltage operating window. And in those cases, we limit battery charge voltage to either 15 in a 12-volt system or 30 in a 24-volt system to prevent damage from the load. And one other mention of the telecom mode, this is a little hard to see, but if you look just to the left of the green charge status LED, to the right of the temperature sensor, you'll see this small little wire loop. If you do have noise in the system, you can cut that wire loop and change the switching frequency of the controller so that it doesn't interfere with telecom loads or other sensitive loads. This is definitely a last resort. I'd always recommend going through a troubleshooting list that we have and can send to you before you go to that extent, but it's there if you need it. And the last thing I'd mention is the load overcurrent and short circuit protection. Just an indication here, there's a lot more to this. Don't have time to get into it too deeply, but did want to mention that we do have quite a bit of inrush factor of safety built in on the load terminals for the Sunsaver Gen 3. As you can see on the 20 amp model, you have almost up to 180 amps of inrush that it can accept for short duration, a short burst, but to let you operate loads that might have those inductive loads that might have those kinds of inrushes without an issue and still have the benefit of LVD. If you run into problems with this, we have a white paper that's written and details some specific remedies to getting around those inrush currents and, in a sense, protecting the controller on this load terminals from having a problem running those loads. We can certainly, if you have questions, give you some information about those after the webinar. And real quickly, just to wrap up on the controller section, did want to mention just a couple of points on PWM versus MPPT controllers. Now, in hazardous locations, of course, we require the Class 1 Div 2 rating, and that limits us to the PWM side of this chart. But if it's acceptable or outside the zone or places where that HAZ location rating is not required, you can consider MPPT controllers. There's some benefits to doing so. It's not required for, it's not to say that PWM controllers are in any way inferior, but you do get some better options for module compatibility, data and communications abilities, metering interfaces and such. So I just wanted to mention this. Hopefully we'll have another opportunity at a different date to get into MPPT in depth with you. But just mentioning a couple that we have, if you can mount them outside the zone or not subject to the hazardous location ratings, there is an MPPT version of the Sunsaver with the same footprint. 12 and 24 volt auto detect up to 400 watts. Really high peak efficiency, 97.5%. Getting a little larger into the ProStar MPPT range, we have both metered and non-metered versions, and these go up to about 1100 watts. A lot of field programmability, self-diagnostics, data logging, things that just aren't possible with the Sunsaver. And then as far as larger systems go, up to 3200 watts on the TriStar MPPT. So to summarize, just wanted to say that, again, Morningstar have been at this for quite a long time, 20 or more years in the business. I can't emphasize enough that you need a reliable controller to successfully operate your solar system. And this is something that we take very seriously. There's only one thing we do, and that's off-grid, reliable off-grid controller design. And so to the extent possible, we're always trying to make sure that your loads are always up. However, I do still want to emphasize that there's still no substitute for proper system design. There's only so much we can do with what we have, and this is the starting place, the starting point for any system. If we had more time today, we'd get into this a bit more, but I think that's a topic for another day. So at this time, I'd like to turn it over to Ken. He's going to talk about wind and give you an overview of the Primus air turbine line. Ken?
Great, thanks, Kyle. All right, well, you guys should all be able to see my screen. Again, this is Ken Kodalik talking to you from the lovely town of Flagstaff, Arizona, and all my contact information is right here on the screen. And just as Morningstar did, we would like to start with a poll question as well regarding the turbine and how it may be used in the field. So you should be seeing on your screen now a poll question about how you're currently deploying what we're going to talk about today, which is hybrid systems, if you're doing that or not. And that's a big part of what I'm going to be chatting about today, along with the operation of the wind turbine. So please go ahead and answer one of those A, B, C, or D questions and let us know. And Kyle, when you're ready, we can go ahead and give you the results of that poll question.
So right now we have about 50% voted. Give it a few more seconds.
Okay, and so just let you know as you're voting, what we're going to be talking about is the air turbine and the functionality of it, and as well as what's new in the industry and what we see a lot happening, especially in the last year and a half or so in oil and gas, is combining wind and solar together for a hybrid system. And it makes a lot of sense, and I'll kind of explain to you why it makes sense and how we use the air turbine in that operation.
So the poll's closed. We got about 80% voted. Appreciate that. 41% solar only, but a good portion, 21 have used a few, but not to great extent, and 13% definitely used hybrid systems quite a bit. 25% considering hybrid systems as an option.
Great. All right. Thanks, Kyle. So just a little bit about Primus wind power. Some of you guys might remember, if you back in the day, that we took over from Southwest Wind Power, who was manufacturing the air turbine for many, many years. But in January 2013, unfortunately, Southwest Wind Power went out of business. Their manufacturing facility in Flagstaff, Arizona closed, and we took over. We have a manufacturing facility in Denver, Colorado. Our company's been around quite a long time, since 1989, primarily working in the aerospace industry. So building a wind turbine for us was an easy transition, and so we have both the aerospace side as well as the wind side of our business. Again, made in the USA, U.S. manufacturing out of Denver. Let's look at the turbine itself. So it's called an upwind horizontal axis turbine, and let's go through the components of it so that you understand it. So the wind direction blows in from basically this direction. The nose cone is there for several reasons. It's there obviously for aesthetics, but more so to direct the laminar flow of wind across the blade set. It is a 3-bladed turbine, and it also helps to keep any water infiltration in through the shaft if you have horizontal blowing water, which you can. And so it's good to have that nose cone on there for all of those reasons. So if it pops off, make sure you get a replacement for that nose cone. 3 blades, they're balanced blades, so if there's ever a crack or a nick or a ding or anything significant in one of the blades, very good idea to change it out as quickly as possible, because it can damage the turbine and obviously reduce the operation efficiency of the turbine. Here's your hub right here, sealed bearings, face of the turbine right here, stator isolator pad. Here's your stator itself with the copper windings. This is your neodymium magnets surrounding your shaft and your rotor right here. The stator actually produces what we call wild AC, unregulated AC, and then as that unregulated AC goes into the circuit card, there's a rectifier block that rectifies that wild AC to 12, 24, or 48 volt DC. The turbine is voltage specific, so you have to match the voltage of the turbine to the voltage of your battery bank. It's not field adjustable for the specific voltage of the turbine. There are field adjustability within the potentiometer, which I'll talk about here in a minute, but you do have to buy the turbine voltage specific. This is your potentiometer harness. There's an O-ring that seals the face and the nacelle, the body of the turbine here, and then your sealed bearings and your yaw assembly. The yaw contains the brushes and the slip rings, which allows the turbine to spin 360 degrees to keep the turbine, as we say, on the wind. The turbine direction of wind, again, is this way. It flows in across the blade set, across the nacelle, hits the tail, and allows the turbine to stay on the wind, especially in turbulent environments like we often have in oil and gas settings, because there's lots of equipment and so on. So that ability for the turbine to stay on the wind is really important. So what's exported down tower is DC power. Okay, DC power. The turbine is, all the control electronics are up tower. We call it up tower controls. So there's nothing down tower other than the fuse and the breaker and a few other things we'll talk about. But all the control electronics are done up tower here in the nacelle, allowing DC power to come down to the turbine. So it keeps it very simple, not complex for installation. If you ever want to see inside the turbine, and I highly recommend you to go to our website, primuswindpower.com, go into the support tab, and under the support tab, under service repair, you'll find really great videos on troubleshooting, basic cleaning and maintenance, circuit replacement, basic installation of the turbine. If you're installing this turbine, or if you haven't in the past, or if you have in the past, these are great videos to watch. Short videos, but well worth your time, because there are some important tips and tricks for when you're installing this turbine. Here's what you get when you get one of our air units. This is a land unit, typical for oil and gas. It's the aluminum housing. On the side of the turbine right here is the potentiometer screw. I'm going to talk about that pot screw here in a little bit. On the bottom of the turbine here is the LED light. It's a little bit hard to see, but either a red or a green LED. And if you ever call into tech support, one of the first questions they'll ask you is, what's the LED activity? So you need to, when you're looking up at the turbine in the field and you see that LED, you got to pay attention to what that turbine, what that LED is doing. All this information is in the manual, but I want to briefly review the LED activity. When you first install the turbine and you connect it to the correct voltage battery bank, you're going to get two slow blinks. That will say that your turbine is connected, it's recognizing the battery voltage, and the circuit card is recognizing that. Then as the turbine spins up in about a 7-mile-an-hour wind and spins up above about 400 RPMs, you'll start to see exporting energy, exporting power down to the battery bank. It could be just a milliamp or a quarter amp, but the LED will then become solid. As the battery bank senses, as the circuit card senses that the battery bank voltage is coming up to full, and for a 12-volt system, the factory setting for that is 14.1 volts. The LED light will then begin to blink slowly. It'll blink slowly until the battery bank voltage or a load goes down or a load comes on, and then it'll go back to charging again. The turbine is essentially a bulk charger. It is on or off. The finesse charging is done by the solar. That's why we work so well with Morningstar. We're basically just bulk charging for the winter months, storm periods, times during the summer when you don't have as much wind because of storm periods or weather. We're basically providing that bulk charge for your battery bank. So when it senses the battery bank is full, it'll slowly blink. The last indication of that LED is overspeed protection. If the wind is above about 35 miles per hour, then the turbine, to protect itself, will go into overspeed, and that LED will begin to blink rapidly. The circuit card will then send a direct short to the windings, and the windings will slow the blade set down, and that's how we control what the turbine is doing. So again, that's the functionality of the LED. We'll talk about this pot setting in just a minute. 3-bladed turbine. This is an Air 40 turbine. Stator isolator pad goes inside of here, and the yaw, nose cone, hub, all the hardware you need to install it. Tef gel, important to put on your blade bolt screws, your warranty, 5-year warranty, and your manual. Installation of the turbine, installation of the blade set, very simple. Blades connect to the hub, to the hub, and then the hub assembly onto the rotor. Jam nut over the rotor, and then your blade, or excuse me, your nose cone snaps onto your rotor. This is a hybrid system, autonomous from your PV solar, right? You got your controller going directly into the battery bank, then you got your turbine going directly into the battery bank, separate systems. This is uncommon. We don't see turbine-only system for an off-grid system because it's so much better to work with a hybrid system. And again, here you have your PV solar array, charge controller, down into your fuse breaker, battery disconnect into your battery. On the opposite side, on the separate side, you have your turbine going through, again, a stop switch. I'll talk about that in a minute. A fuse or a breaker, an amp meter if you want to add that amp meter into your system, and then into the battery bank. Two separate systems that work really, really well together. Stop switch is important. I recommend that you add a stop switch. All of our marine turbines come with a stop switch, but our land turbines, an expensive part, but you can purchase that. They're good for a lot of reasons. Number one, when you go out to the site and you want to do your annual maintenance or you want to check on the turbine, good to stop the turbine with the stop switch. It's a direct short to the windings, and you can do your maintenance. It's also good for a hard reset of that circuit card, which is basically an electronic component. If you have to turn the turbine off for any other reason, big storm conditions or whatever, it's a good idea to have that stop switch in line. Lots of good reasons to have a stop switch in the system. So highly recommend, if you can, very small part, but good idea to fit that into your system. Here's that potentiometer we were talking about, that adjustment screw. Here's the factory set points right here of the turbines at the various voltages, but it is factory settable. Now, as Morningstar and I have worked closely with Trojan and AGM batteries, which is primarily what is used in the oil and gas industry, we have decided and discovered that really for oil and gas, it's better to have this factory setting a little bit higher, 14.3 or 14.4 for a 12-volt system, for example. And so you can turn that pot screw up, and here's the adjustment ranges right here. All of this information is in the manual and exactly how you do that. And so for an AGM battery, that's usually a good idea. It's a very simple thing to do, and it brings the turbine into more of the absorb stage of the battery, and especially with the AGM Trojans. So that's why we recommend that you consider doing that. I can certainly talk to you more about that offline if you have questions on that, but that is a recommendation. Here are the factory set points for just kind of FLA, flooded lead acid batteries, but for an AGM, that might not be a bad idea. Here's the specs of the turbines, a 5-year warranty. The startup, or what we call the cut-in speed of the wind turbines, are right here, and so that's important to know because when the turbine is in operation, you may think you have enough wind, but you really need to have about 7 or 8 miles per hour of wind for that turbine to start operating and sending power down to the battery. It is what we call a micro wind turbine. It's a 1.2 meter rotor diameter, 46-inch blade set. That's the diameter of the turbine. Very light, 13 pounds, so very simple installation. 1.5-inch pipe, 1.9 OD is what is accepted into the yaw. You can see in this picture right here, there's the yaw, and the pipe slides right into it. A little bit about tower height. Most oil and gas industry towers are, really quite short, 10 to 15 feet in the air. But because most of those sites, West Texas, North Dakota, and so on, have really great wind resources, it's not as necessary to go as high. But as you can see here, as you go up in tower height, assuming laminar flow wind, you have an exponential increase in energy production, 20% going just from 10 meters to 4 meters. So something to keep in mind. More importantly, siting is important. I've discovered in the oil and gas industry that there's really, you don't have much of a choice of where you put that turbine. So but if you can site the turbine on the prevailing wind side of any object that's going to cause turbulence, like a building or equipment, that is the best place to put the wind turbine for the optimal energy production. So, you know, that's something just to keep in mind. Generally here in the Southwest, in North America, the wind direction comes out of the Southwest. So keep that in mind. A little bit about hybrid systems. So I have solar on my house here in Flagstaff. It's great, but you know, there are some disadvantages, right? Solar has low output during the winter months, diminished output during bad weather, and no output at night. And so that's where wind power takes up the slack. We have the higher wind speeds are in the winter months. Air density is higher in the winter months, which helps to increase power output of any turbine, because as you can see here in the equation for wind, air density is a big part of it. Wind velocity, obviously, wind speed is the most important. It's cubed. That's the most important. And also the swept area. That's how much wing you have in the wind, as we say, the rotor diameter of the turbine. Wind, on average, is stronger during bad weather periods. As we say, when there's weather, there's wind. And it does frequently blow on those long winter nights. If you've ever been to North Dakota in the winter, you obviously know that. This is kind of the crux of the argument right here. Wind and solar are very complementary. It's like Mother Nature telling us to combine the two together for off-grid systems. In the summer, lots of solar, not a whole lot of wind. Many places across North America is the opposite. In the winter, lots of wind, not a whole lot of solar. This is a map of the United States. The darker the blue color, the higher the wind speeds. You can see here throughout the middle portion of the United States, lots of good wind. That's why the utility scale wind turbines are mostly located here. On the coastline, lots of good wind here in Texas, North Dakota. The mountain regions have obviously good wind speed. So lots of places across North America have great wind. So very good idea to deploy a wind turbine as long as you have about 10 mile an hour of average winter wind speed. In a hybrid system, we only focus on winter wind because that's when you need the help, is in the winter when the solar is not kicking in as much. So we focus on winter wind speed. Here's just a little diagram basically saying that during the colder months, you can increase your energy production, your power production out of a wind turbine because the air is more dense, somewhere between 5 and 15% likely energy production increase. This is using NREL data for sites across the U.S. Pick 3 sites. You can see here in Rapid City, South Dakota, the old saying, when there's weather, there's wind, truly holds true. Not all the time, but on average, when it's more, it tends to be, when it's more windy, you tend to have, you know, poor weather. Amarillo, Texas, a little less pronounced, but Cheyenne, Wyoming, obviously well pronounced as well. Here's a little actual complementary curves, again using 30 years of NREL data. Most pronounced here is Billings, Montana. Lots of sun in the summer months, but not a whole lot of sun in the winter months. And you see this curve, and which makes sense to add wind and solar together. If you've been installing solar for very long, you know that there's a huge difference between June and December for the solar day. That's why you size your system for generally December 15th, the shortest day of the year, the mid-December region, because of the fact that you know you're going to be reducing that solar potential. But if you have a wind turbine in the system, you can completely change that paradigm, so that's why we commonly recommend that. Nighttime power production from a wind turbine as well is important. And here's the crux of the argument, really. You know, you're trying to lower that depth of discharge into that battery bank. So if you have a wind turbine in the mix, you're not going to be deeply discharging the battery in the winter months during storm periods and so on with a wind turbine, because you know you're going to get some power production, energy production into that battery bank. This is the crux of the argument. This is a Trojan brochure right here. Just a little bit about air. You know, been around for a long time. 1995 we started, made lots of improvements. Today we have a very reliable, very robust turbine. That's why oil and gas primarily uses our turbine. It's American made, been around for a long time, parts are easily available, and it's robust. These are kind of the difference between the blade sets between the 30 and the 40. We typically see in most locations now oil and gas because of the short towers that we're using the 40, but the 30 has some advantages in very high wind speed locations as well. Happy to talk to you more about that. as well, but typically what we see for oil and gas is the Air 40. Let's just show you some pictures to finish up in the last couple minutes I have before questions. Here's a 45-foot guide tower, small cabin, turbine spinning away. Remote location here, Himalayan steppes. Very good wind resource here, zero surface roughness. You can see very good place for wind, as you can imagine. A lot with the sailing industry, just a fun picture here. We do quite a bit with sailing and parking lot light applications as well. Obviously makes a lot of sense because you're using that energy at night. Here's oil and gas, Colorado and Wyoming here. Short towers, as you can see, but again, very little surface roughness, so these turbines work really well because they are getting good laminar flow wind. This is a power skid. This is a self-supporting lattice tower with a stub pole of the 1.5 schedule 40. No more than 6 foot unsupported we recommend on 1.5 schedule 40. And this is a portable energy platform essentially for typically used in oil and gas. This is mining industry on a tailings pond here and remote movable applications there on the trailers. This is, if you can guess where this is by the solar panels. This is the bottom of the world, Antarctica, by the vertical solar panels. If you're using multiple turbines, then we recommend that you put them at different elevations so that you don't have a downwind shadowing effect on the downwind turbine, which would be this one. So that's why these turbines are at multiple heights, so that you don't have that problem with not having or having less power production on the downwind turbine. Again here, this is a buoy platform, solar and wind, again at different elevations to minimize that downwind shadowing effect. Here's telecom. We see a lot of this, especially in Africa and emerging countries. Railroad applications, especially positive train control. They used to use propane with generators. Now they primarily use solar and wind. RV application, I just like this picture because of the Palapa and the Sea of Cortez. We'd all like to be there, wouldn't we? And then here is Alaska, the turbine spinning away with the solar panel not doing so great. All right, there's my information, and I'll turn it back over to Kyle. But finally, there's my information. Thank you very much for being on this webinar today and taking the time to be with us. I'm available to you for questions and follow-ups. Thanks again. Appreciate it.
Well, great, Ken. Thanks a lot. Why don't we handle, we've got a few minutes, why don't we handle a couple of questions that have come in here. The first one is for you. Are any of your turbines UL listed?
Yes, they are. They are UL listed. You can see that on the website. We're also going through final testing right now at the UL facility in Canyon, Texas. And they are certified not only UL for but also for Canada, CSA, and some other European certifications.
Very good. Yeah, there's quite a few coming in. How about this one? Another wind question. How long can a turbine be left in the stop position? And the second part is, how severe of damage would occur if that was left in the stop position longer than the recommended period?
The turbine can be left in the stop position pretty much indefinitely. It's just a direct short to the winding, so it's as long as it's connected to the battery bank. If it becomes disconnected from the battery bank, then you know that there's potential for open circuit. So you want the turbine connected to the battery bank and in the stop position. There's that stop switch I showed you about has 3 positions. The middle position is open circuit, and you never want to leave it in that middle position. So you want to flip it from run to stop and come right through the middle position. So it can be left in that stop position pretty much indefinitely.
Very good. Let's see what else we have here. Got a couple more minutes. Here's one. Are all the products mentioned usable in Europe according to CE laws? I can say definitely for Morningstar. And how about the air turbine line, CE certification?
Yes, it is, and we are, again, going through NREL testing to get additional European certifications. We have a European division in Germany, So I can certainly connect that person up with our European division in Germany to talk more about all the different certifications that are available.
Yeah, and I would say just that on the topic of certifications in general, this is something that both Morningstar and Primus take very seriously, and I think stand out among the world of manufacturers in these areas for going after and seeking the highest standards and certifications. So I would say just check back regularly to each of our product pages for updated listings. Right now we're undergoing pretty extensive certification to a lot of the IEC standards. 62109 applies to much of the world now and is increasingly becoming more of a global standard. That's another one that's come up quite a bit and will certainly exceed the requirements, the testing requirements of CE or even in some cases UL. So there's quite a bit of activity in that realm, and it's really important for certainly our customers to have the right documentation in hand there. We're getting close to the time, but I think we probably have time for one or two more. There's a lot of you that are asking questions. We're definitely not going to get to all of them on the webinar, but we'll cover what we can and address everything else offline. So Ken, what about maintenance? I know you talked about maintenance a little bit, but can you tell us a little bit more about required maintenance on your turbines?
Yeah, great question. There is a webinar I alluded to on, there's a video on our website for maintenance on a turbine, but I can say that the turbine every 12 to 18 months is a very good idea to take 5 minutes, go up to the turbine, take a look at the blade set, look for any significant nicks or chips, and if there are, you have to replace the entirety of the blade set, all 3 blades. It's relatively inexpensive to do that. You also need to look, pop off the nose cone, tighten the connections between the blade root and the hub, make sure those are nice and tight. Tighten the connections between the yaw and the pole, the yaw connections, very important to do that. Just make sure the turbine spins 360 degrees and that nose cone is on nice and tight in all 3 quadrants. And other than that, that's really all you have to do for maintenance on a 12 to 18 month basis. Very simple, literally only takes 5 minutes or less to do that, but we highly recommend you do that for the longevity of the turbine.
Very good. Yeah, I'd say on the same topic for SunSaver or most of our controllers, it's pretty much consistent that there isn't much in the way of field repairability. There isn't any on the SunSaver if you have that solid status light red with a heartbeat. It will indicate a damage that has to be replaced through warranty. But on some of our other stuff, there's the possibility to replace only a handful of components. In general, they're solid-state devices, relatively maintenance-free, only field repairable in a very small set of circumstances. I think we have time for just one more, and I want to address this because I didn't quite get to a lot of it in the presentation, and that is just what's the meaning between PWM and MPPT controllers. This is a great question, deserves its own webinar, and in fact we've dedicated quite a bit to some recordings that are available on our website on this topic. I'd encourage you to read, but real quickly in general, just it's a completely different architecture. PWM is a series type controller passing current through pulse width modulation directly from PV to battery, whereas MPPT is actually a DC-DC conversion device. Typically we refer to it as a buck converter. It takes a voltage at a high level on the solar side and converts it to a lower level on battery, and in the process converts power. And that's where we see the boost that comes from this power conversion. When we refer to a 5 to 20% boost, it's because we're converting power, and it will often result in a higher battery charge current on the output side. There's quite a few more. Really appreciate all the questions and your attention today, your attendance, and would encourage all of you to visit both of our websites here. Of course, Ken and I both welcome emails anytime if you have further questions or want to chat more on any of these subjects. In the interest of time and to be respectful of everyone's day, I do want to close out the webinar now. Just thank you again for attending. It is 1 o'clock, so we'll end here. And again, thanks a lot. We'll have a recording of this webinar available on our website. Have a great day, great weekend, and hopefully we'll see you all soon. Thanks again.